Look at a handful of ordinary sand. It costs nothing. It is the definition of mundane. But if you take that sand, melt it, purify it to a factor of 99.9999999% and slice it into wafers thinner than a human hair, you cross a threshold. Welcome to the $1 trillion club. Today, the global tech economy isn't driven by oil or gold, it's driven by silicon chips so advanced that a single wafer can dictate geopolitics, and a single architecture can spark a multi-trillion-dollar market rush. But behind the eye-watering economics lies a brutal reality. We are running out of room. To make artificial intelligence smarter, we have forced humanity's most complex engineering up against the absolute, unbreakable laws of quantum physics. For 50 years, the semiconductor industry followed a simple gospel: Moore's law. Double the number of transistors on a chip every 2 years. Make them smaller, make them faster, make them cheaper. It worked beautifully until we hit the nanometer scale. To understand how small we are talking, a single strand of human DNA is about 2.5 nanometers wide. The leading-edge transistors pumping inside the world's most valuable AI hardware are smaller than that. A transistor is nothing more than an electrical switch. Apply a voltage to the gate and electricity flows, that's a 1. Turn it off, electricity stops, that's a 0. Simple, right? But when the barrier of that switch is only a few atoms thick, classical physics breaks down. Enter the ghost in the machine, quantum tunneling. At the atomic scale, electrons don't behave like solid billiard balls, they behave like waves of probability. When a barrier becomes too thin, the electron simply says, "I think I'll exist on the other side now." It leaks through. This means the switch can never truly turn off. The chip starts wasting massive amounts of power and generating catastrophic heat. We didn't just hit a manufacturing wall, we hit a quantum wall. So, how do you print features smaller than an atom without breaking the universe? You don't use mechanical drills or traditional lasers. You use light with a wavelength so short it practically doesn't exist on Earth. Extreme ultraviolet light, or EUV. To print a $1 trillion chip, machines built by ASML drop a microscopic bead of molten tin, flying through a vacuum at hundreds of miles an hour. A high-power laser blasts it. Then, a second laser obliterates it into a plasma cloud hotter than the surface of the sun.